Thank you, Volker. Many thanks to the organizers of this excellent program for giving me the opportunity to participate, and also to the organizers of this workshop for inviting me to give a lecture here. And why have I chosen this topic, gamma distributions in Poisson Voronoi and hyperplane tessellations? Okay, it's due to this keyword, tessellations, which have found in recent years widespread use in spatial communication networks. So let's go just to the very end of the talk. So you will see here a few references on the application of stochastic geometry in modeling and analysis of wireless networks. There's some work of François Bargelli, Bartek Plaszczyn, and others. And they have even a book now on applications of stochastic geometry. There's another group working on application of tessellations from a stochastic geometry perspective, working around Volker Schmidt in Ulm. And there are others, of course, sorry for not mentioning these names, but we all believe, I think, that spatial tessellations and the mathematical approach to this theory is very useful when it comes to actually analyzing stochastic models in communication systems. So let's go back to the beginning. So it's about gamma distributions, and I think it's fair to give first some overview about the historical background here. So it's on gamma distributions in stochastic geometry, okay? And I'm listing here some of the seminal papers on the topic. And when lecturing about stochastic geometry, it's unavoidable to mention the name of Roger Miles, who made really significant contributions in probability theory. And it was him who came up with the first results on gamma distributions. He called it complementary theorem for some reasons which might be clearer at the end of my talk. So there are several papers by him here. And then there is a nice paper by Jesper Müller and Sergei Zuyev back in the 90s. And this is also a sort of seminal paper because this opened the way, or actually this paper has established a modern approach to Miles' result using prime calculus and modern language of mathematics. And Sergei has a later paper where he came up with other but related gamma type results. And then more recently, Lutz Muche, who was a former PhD student of Mecke, of Stoyan. He did this Dietrich Stoyan. He found some interesting gamma distributions in Poisson Voronoi distributions, and me and my student Volker Baumstark have derived this in a more general context. And then I started wondering some years ago about the general pattern behind this gamma distribution results. So there are results that come from complementary theorem and its generalizations, and there are results which come from stopping sets. So I was wondering about the pattern. I asked my student Volker to work out the details, and he did it for Poisson processes of points, and later on I generalized this to Poisson processes of flats. I'm not sure whether I will have the time to speak about Poisson processes of flats. We will see. Friendly reminder of the gamma distribution. What is a gamma distribution? It comes with two parameters, namely with the parameter alpha, which is responsible for the shape of the distribution, or the density, that's the density, and this is just a scale parameter. And a few facts about the distribution. If X is gamma distributed, then it comes with this mean, with this second moment, and with this variance. Uh, middle term might be wrong.
No, lambda squared.
This is lambda squared, yes. Thank you. You are very attentive. Okay, thank you. I've noticed this. And it has these nice convolution properties. If you add two independent gamma variates with the same scale parameter, then you end up with a gamma distributed random variable with the same scale parameter and with the shape parameter given as the sum of the two original parameters. So this is a friendly reminder. And I would like to start with a very trivial, almost trivial observation just as a warm-up. Okay. So in most of the talk, phi will denote the stationary Poisson process on RD. If time is left, then I will talk a little bit about Poisson processes of flats in the very end of the talk. But for most of the talk, just look at this simple object, namely a stationary Poisson process with a fixed given intensity, positive intensity lambda. So let's do the following. Take a point x in the state space, place around a little ball of radius t and let the ball grow until you hit the first Poisson point. So we look for the first, if you like, time instant t such that the ball centered at x having radius t contains at least, and in fact with probability 1, then exactly 1 point. Then the volume, this denotes volume, of the ball, which is given as a constant times the d's power of the radius, is an exponentially distributed random variable. Why is this so? Okay, as I said, it's trivial, just as a warm-up. So if we are interested in the probability that the volume of this ball exceeds t, so in this probability here, this is this probability, and so this time, growing time, is larger than this time here, if and only if the ball centered at x and having this radius contains no point. This is an empty probability of a Poisson process, so it's given by this exponential formula here. So we see the volume of the ball has a gamma distribution. First example. To give you two other examples, I would like to remind you of the notion of a Voronoi tessellation, which is, I'm sure, well known to all of you. So this is a finite point pattern of blue points in a square here, and we construct a Voronoi tessellation on it. That's following thing. It's a tessellation or a mosaic dividing the space in convex regions, actually convex polytopes. And for instance, this cell here, it's called Voronoi cell with this center, is formed by all points of the plane whose distance to this center is at most as large as the distance to all other points, Poisson points. So this is the Voronoi tessellation. Now imagine that we have given, also just recall that we have given a Poisson process in the whole plane, and we can do the same thing. We can construct the Voronoi tessellation based on this stationary Poisson process. And now, instead of choosing a fixed point x and let the ball grow until we hit the first point, in other words, instead of fixing some arbitrary, choosing some arbitrary point in space because of stationarity, any point x is equally good, we choose one of the vertices of the Voronoi tessellation at random. Okay? So maybe there is some restrictions. Customers are only located at these points. We would like to know something about the distribution to some station represented maybe. Customers are located at the vertices, and we would like to know something about the distribution of the distance to the, let's say, antennas or something like this. So what can we say in this case? As I said, you can't avoid Roger Miles here. So we do the following. Okay. We have a Poisson point pattern, so completely discrete white noise. We form the Voronoi tessellation and pick one of the vertices at random. This can be made precise using prime measures, but informally it should be clear. And then we blow up a ball until we hit the first point of the Poisson pattern. And actually what we meet are 3 points, because we are sitting in a vertex. And a vertex has, by the very definition of a Poisson, of a Voronoi tessellation, the same distance to 3, we call it neighbors. Okay? Is this clear? I think yes. Huh? This vertex here has the same distance to 3 points. This vertex has the same distance to 3 points. And this vertex is characterized by 2 properties. Namely, there are 3 points on the ball centered at this point. And in the interior of the ball, there's no other point. Okay, let's form the volume of this ball. No surprise, because of the title of the talk. It comes with a gamma distribution. However, with a different shape parameter. So in the plane, it's a gamma 2. So of course, this volume is stochastically larger than the volume of a ball around some fixed deterministic point. But it's very nice that we know exactly how large it is. Even more, it's gamma distributed. It's a Erlang 2 distribution, if you like. Okay, so let's make a third experiment. So in the first experiment, we have chosen some arbitrary point in the plane. In the second experiment, we have chosen some arbitrary vertex. In the third experiment, we choose an arbitrary point on the segments, on the edges of the Voronoi tessellation. So how to do this? In this case, we could just use the uniform distribution on the edges. So we choose such a small infinitesimal interval with a probability proportional to the length of the interval. And we blow up the ball, and then it's clear we have 2 points having the same distance, because any such edge here consists of points having the same distance to these 2 Poisson neighbors. And somehow the distribution of the ball containing these points in the boundary should be somewhere in between stochastically. It should be smaller than the corresponding ball put around the vertex, but it should be bigger than the distribution of than this exponential distribution. Indeed, it turns out it's a gamma distribution with parameter 1.5. So that's interesting for several reasons. First, it's interesting, it's again explicit, it's a gamma distribution. Second, it comes with a fractional parameter. So it's a gamma 1.5. And this is actually a more general result. So we are in d dimensions here all the time. So instead of picking a point on the edges, we can pick also a point in 3 dimensions on the faces. Or in d dimensions, we can pick a point on the j-dimensional faces. Okay? And then you come up with this result. If you put here d equal to 2 and j equal to 1, it is 1/2. You observe here, if you look at this shape parameter, if j is getting larger, vertex, edge, facet, and so on, this number becomes smaller, and as it is intuitively obvious, I think, things are stochastically decreasing in j. Okay, let's take this as a motivation. Later in the talk, I will have much more examples for gamma distributions. So now let's do a little bit of mathematics. This was sort of story, you know. Let's do a little bit of mathematics. So I would like to show you a pattern for all these gamma distributions, and I do this in 2 steps. In the first step, the sets whose volume are being considered are depending on points and not on the configuration. Later on, the sets will also depend on the configuration. So there are a lot of ingredients now. I just try to focus here a little bit. So there are some parameters, m, n, j. J we have seen before. N is m and n are given given integers, non-negative integers. This is a constraint which is always satisfied. So the main object in the talk is this guy here. It's a closed set. it's a closed set, and it depends on n points x1 up to xn. Later on, this will be Poisson points. So I'm choosing later n Poisson points. So for instance, in this vertex, in this Miles result, I'm choosing 3 points. And this set depends also on x. Okay? So we have a set S which depends on x1 up to xn and on x. And this dependence is, geometers call it equivariant under translations. It means the following. If we shift the points x1 up to xn and x, the result, and apply the set S to the shifted to the shifted points, then we get the shifted set. So the set is not invariant, but it's equivariant. If we scale the points, it's very important now. If we scale the points, for instance, by multiplying any point with 1/2, then we get as a result 1/2 of the original set. So it's equivariant under translations and scaling. These conditions can be relaxed, taking into account probability measures, but for the purpose of this talk, it's okay, I think. So I don't need this. I need translations and scaling. And in some of the examples, you have rotational equivariance and some not. So why should I make this assumption? I don't need it. So then there is a function R, which has the same arguments, and in addition can depend on the configuration phi. This is some sort of indicator function. Also, for instance, to give you an example, in case of the vertex, this will just, if we choose 3 points, also as a rule, they will not form a vertex because there will be other points inside the corresponding ball. But then we just put R to be the indicator that there is no point in the ball, and then this way we can select really vertices. So this is a sort of indicator function, and this is assumed to be invariant. And then there is a measure mu depending on x1 up to xn, which is translation equivariant and which has a very important scaling property. Without this scaling property, we are lost. Okay? So in the Roger Miles example, the j was equal to 0. This is due to the fact that the mu is just sitting in one point. To be more concrete, it is sitting in the center of the ball. In the first example, j was equal to d, and in the example with the edges, j was equal to 1. And you see it has something to do in all these examples with the dimension of the Hausdorff measure we are using. Right? The first example we were using volume. In the second example we were using just counting measure. In the final example we were using one-dimensional line length. So the scaling is j equal to 1. Okay, these are the ingredients, and what we are doing now is the following. It applies to all the examples you have seen before, and later on in a more generalized version it applies to all gamma distribution results we are aware of for Poisson processes of flats. So what we are doing now here is we look at the volume of this set. So this is the indicator function that the volume belongs to some Borel set C. So I have to be a little bit more precise now. And what we are doing is first we are weighting this with the function Rm, which is the R with the additional property that it's only 1 if the point pattern contains m extra points in this set. In the previous example, m was equal to 0. Then we integrate the x with respect to this mu, and then the most important step is we sum this up over all different n-tuples of the Poisson process. So we are summing up over all n-tuples of Poisson points. What we get in the end is a random measure in 2 arguments, because we are summing over, we are performing the integration with respect to x only over the set B. So it becomes a measure, it becomes a random measure, because everything depends on the Poisson process. And it's actually what people call stationary random marked measure. So if you fix the so-called mark set then the distribution of this random measure in B is invariant under translations. And under all these assumptions I've mentioned, the following is true. The so-called mark distribution of this M, and I will tell you what it is gamma. So M plus n, these n is the number of miles called it particles. So points, Poisson points, is here. That's the dimension. That scaling j of this mu, and this is the number of extra points which might be contained here. This is governed by this Rm. And because I got 1 hour, this is more than this lecture, I thought I'd give you the idea of a proof, to show you one proof at least. Maybe it's the only proof today, I don't know. I would like to do this just to give you a flavor of the arguments, and it's if you like, it's a festival of invariance arguments, okay? So first of all, I would like to give you the definition of this mark distribution. It's not difficult. It's the following. It's just based on the expected, no, I'm not allowed to do this, I'm sorry. Something changed? Huh? So this is general stuff now. We have a random measure on Rd times R plus. You remember, hopefully, that this is describing R plus is describing the volume, okay? So it's a random measure. This is called intensity of this stationary random measure, that it's the mean, the expected mass in a set of volume 1, okay, ignoring the marks. By stationarity, the intensity measure itself factorizes in a product of the intensity, Lebesgue measure, and some distribution on the non-negative reals. And this is what is called mark distribution. It's a one-line proof that this is true, just because Lebesgue measure is up to a multiplicative factor, the unique measure on Rd, which is translation invariant. So you can do this actually for any stationary measure on a product of a group carrying a unique Haar measure times basically arbitrary space. So this is this is the standard definition of the mark distribution, or Palm mark distribution, or Palm distribution, or whatever you would like to call it. And the claim is that this V, for some mysterious reasons, is a gamma distribution. Okay. So we need to prove this. So what are the arguments? So first of all, we have to work a little bit now. Let's say 6 minutes. So first of all, we have to recall the definition of this mark distribution. As I said on the previous transparency, this mark distribution here, if you replace dt by a set, and if you divide both sides by gamma m, you see the mark distribution is just this thing. It's a very intuitively appealing formula because that is the mean expected mass of the random measure, with points being in a unit volume, and the mark belonging to some specified set C, suitably normalized. This is just a normalization needed to make it a probability measure. So then there is the only probabilistic ingredient here is what we call in point process theory Mecke formula or Mecke-Slivniak formula. It's a formula which is used again and again when dealing with Poisson processes. And to see this, you have to remember that we are selecting n points of the Poisson process. We are selecting n tuples of Poisson points, okay? And we are forming the expectation. And when forming the expectation, because somehow infinitesimal infinitesimally. If you take away a Poisson point from a point phi, then this object is independent of what is happening in an infinitesimal neighborhood of the point x. And we are using a multivariate form, a version of this. So you see here dx1 up to dxn. This comes from the n Poisson points chosen. And because of forming the expectation, this e to the minus gamma, this is a misprint. It should be lambda. That's the intensity of the Poisson process. It should be lambda, I'm sorry. E to the minus lambda t divided by m factorial. This is just because I'm choosing only those points, x1 up to xn, having the property that this set here contains m further points of the Poisson process. And so this is just a probability here. And then these are the arguments. And I have written it in this way for a certain reason. This should be, this m is replaced here by a b because I'm working now with this new b. So this is really just a basic formula for Poisson processes. It's no deep issue. Okay, so the mark distribution can be expressed in terms of this guy for b equal to m. And now comes the invariance arguments. I have made several invariance assumptions on S, R, and mu. Everything here is invariant under translations. And that's why in the first coordinate, just by the very same argument you have seen before, in the first argument, this guy here must be a multiple of Lebesgue measure. In the second argument, we don't know yet. So in the first argument, this is a multiple of Lebesgue measure. Okay, now the trick is as follows. You fix a set of volume 1, this is the unit cube here, volume 1, okay? And you, instead of looking at capital C, you scale the set. With the following idea, maybe I skim over this now. The idea is as follows. If you have a scaling like this here, if this scales, we have seen a lot of scaling in the morning, so it's again a lot about scaling. Everything is about scaling here. It's the right scaling. So the gamma distribution parameters come from the right scaling. So if you choose the b, which is arbitrary so far, appropriately, then you see that you get here just the a. b chosen this way gives just all the exponents add up to 1, and you end up with an a. And now comes the second invariant argument. There's only one measure on the positive reals, forget about the 0, which has this property. The Lebesgue measure again, up to a multiplicative factor. That's because there's only one measure, the Haar measure, which is invariant under the multiplicative group on the positive reals. That's fine. So we have because then we have the second component as well. The whole new b here with the appropriate choice here is just a multiple of Lebesgue measure times Lebesgue measure. Okay. So let's use this now. We can use it only if m is equal to b, but m is not equal to b. So we have to rewrite this in terms of new b, which is an easy thing to do. So we write this in terms of new b, and we get some additional term here. New b is dx times dt. Everything is proportional to this. Forget about the constants. The dx integration yields 1, and we end up with what? With the gamma distribution. And this is the right parameter. If you remember what b is, it's just this. And if you put things together, you get the gamma result. Was a little bit quick, I know, but it was just based on 3 facts. On the multivariate Marquez-Livniak formula, on the fact that Lebesgue measure on RD is the unique, up to multiplicative factor, unique measure invariant under translations, okay? And the fact that the Lebesgue measure on the positive reals is the unique measure having the scaling property. That's all. You've just to know it.
How do you identify the C? Can't you?
Oh, that's the density. I mean, the task is to determine a distribution. So we have the density, and because the density has to integrate to 1, no problem. The C must be the normalizing factor for the gamma distribution. That's the advantage of probability measures. Otherwise, we have some freedom, of course. Okay, so time is running quickly. I give you more examples now. Unfortunately, this argument, or maybe not unfortunately, it doesn't carry through in the general case. I don't know how to do the scaling arguments for more general situations, so we have to resort to other methods. But thanks to others, for instance, to Sergei, we know how to do it. We just need a good setting. So let's give you some more examples about gamma distributions. So we are still in the same setting. We have a Poisson process on RD, and we still work with the Voronoi tessellation based on this Poisson process phi. And we now look at the J phases. These are the J-dimensional phases. For instance, the edges. For instance, the edges in a two-dimensional case. And now, again, I blow up a ball until I have d minus j plus 1 points, Poisson points in the boundary. For instance, if d is equal to 2 and j is equal to 1, then it's again 2. Yeah? This is just the right number of points you have to have by definition of an edge. And then I continue the growth process until I capture another m points. That's easy to guess now. If m is equal to 0, we have this shape parameter. If m is some arbitrary integer, I'm just catching up more exponentials, if you like. It's very easy to see. Something more fancy. This is an observation again made by Roger Miles and a student of him, and made precise and generalized by Jasper Möller and Sergei Zuyev, as far as I remember. So this is the well-known notion of Voronoi flower. That's something interesting. What we do here is the following. We pick one of the Voronoi cells at random, meaning pick one of the Poisson points at random, okay? And so maybe I show you a picture, it's better. Picture can say more than 1,000 words. So this is our cell picked at random somehow. So it comes with certain vertices, 1, 2, 3, 4, 5 in this case. And now put a ball, or in this case a circle, around any vertex, having its radius given just as the distance between the vertex and the center of the cell. So this one, this one, this one. So could be a flower, okay. It's called Voronoi flower, or fundamental region of this cell, for the following reason. If you change points outside, it's a geometric property, not a probabilistic property now. If you change the point pattern outside, there are more points here, yeah, you don't influence the shape of this cell, okay. So, and I put here a star, because later on I will have another Voronoi flower without a star, and this is just the Voronoi flower of a randomly picked cell. Okay, this is the formal definition. You can believe me. Now, under the condition that the Voronoi flower contains m plus 1 points, because there might be other points in this Voronoi flower, this T star D has a gamma m lambda distribution. And this Voronoi flower is more complex now, a little bit at least, because you just need more information about the point pattern around the cell in order to form it. Okay, this is the case where we pick a cell at random, but equally well we could pick just a cell containing a fixed point. It's always what we call in applied probability customer point of view or manager point of view. Okay, so let's pick a point let's fix a point in the plane or in the space, and just look at the look at the cell containing this fixed point. It's called in stochastic geometry jargon, it's called zero cell or X cell, which is of course larger stochastically, has a larger volume. Spatial waiting time paradox, if you like. Okay, and that's the that's a version of this of the waiting time paradox again, indeed, because we just look at the cell containing some fixed point X, form the Voronoi flower as before, look at the volume, and it comes under the same condition as before. It has a gamma distribution, but the shape parameter is not m anymore, it's m plus 1. And this is because of the size-biased sampling, or better to say area-biased sampling. Yeah? So it's much more likely to pick, also the origin belongs much more likely to a cell with larger area than in the case of area unbiased or debiased or whatever sampling. Okay, I skip this. This is the maybe I should say a few words. This is the same thing now for J faces. I give you a picture. That's nice because you don't need a conditioning here. This is supposed to be an edge in the Voronoi tessellation. So this edge has two neighbors. You see, all the points here have the same distance from these two points here. And then there's another point here and another point here. And you see here, this third point is determining the vertex here, and this third point here is determining the vertex here. Well, what we are doing is we place little balls or balls around the endpoints of this edge, whose radii are just given by these distances here. A colleague of mine in Melbourne, was not Kostya, but somebody else, he called it edge bubbles for some reasons. So we have the edges of the Voronoi tessellation and we have these edge bubbles. So we place, on every edge we place these bubbles, okay? Now, it is also a fundamental region because if you change the point pattern outside, you don't change the geometry of the segment. So it's really the straightforward generalization of the Voronoi flower now for edges. And you can what is this doing here? It's doing the same thing for any J. Okay. So we pick a J face at random. We are forming this face bubbles, if you like. If the dimension of the face is bigger than 1, we need to condition. If J is equal to 1, we don't need to condition because any edge has by definition 2 ends only. And it has been observed for dimension 2, it has been observed anyway, it has been observed that this has a gamma distribution, okay? And so much the same as for the Voronoi flower, and we have generalized this to any face and to any dimension. This is a fancy picture, isn't it? That's the same thing for dimension 3. So in this case, we pick a 2-dimensional face of a 3-dimensional Voronoi tessellation. So these black points are Poisson points. This is supposed to be a 2-dimensional face of the Poisson Voronoi tessellation. And you see all the points here, that's a triangle by random coincidence, have the same distance. And here you have, so the other Poisson points, you can't see them. So this is now the union of 3 balls. And this union of 3 balls has a gamma distribution. Again, conditioned on the number of points in the union of these 3 balls. Okay, so you can do the same thing. This was area unbiased, so we just pick J faces at random, not taking into account size. Taking into account size, you get a similar result. Yeah? And now I would like to tell you the general picture. So how to capture all these phenomena? So somehow, what's going on here? We are selecting n points from the Poisson process, and we are forming sets But in these other examples, we have seen that the sets we are forming, these are depending on the configuration. We have to blow up points around vertices until we hit further points. So there's something going on here, and the right thing to do is to capture it is the concept of stopping sets. So I formulate the concept of stopping sets just in the language, and I have to be a little bit more rigorous here. It's no other way to do it. So we let bold n be the space of all locally finite subsets, as identified with counting measures, and we introduce sigma field calligraphic n, and calligraphic nk is then the sigma field containing all describing the information provided by the point patterns in the set K. It's a standard abbreviation. And a stopping set is a mapping that maps point configuration into closed sets in a specific way. Namely, if we would like to decide whether this stopping set is contained in some set K, all we have to do is to check what is going on inside K. Doesn't matter what is happening outside. That's written here. And all we need is a result by Tom Kurtz, and it has been used by Sergei, I think, for the first time in this context. What we are doing now is for instance, we have our Poisson process has intensity lambda. We rescale the Poisson process such that it gets intensity gamma, okay, for some positive gamma. And so this expectation here is referring to the rescaled Poisson process with intensity gamma. If the T was a deterministic set, then this is an elementary exercise in probability. Namely, the distribution of this Poisson process is absolutely continuous with respect to the distribution of this Poisson process. You can write it down, just a few lines of calculation. And the message here is, okay, you can do this also for random sets, supposing they not depend on the configuration in a very complicated way. They are just behaving like stopping sets. So you just can replace a deterministic set by a stopping set in the same formula. It's true. So Tom has, if I'm not mistaken, has used this concept of stopping sets in a more general framework, formulating optimal stopping theorems and things like that. Okay. We are using this formula, it's important. And I don't know how to do it without this technique. I know how to do it in more, as you have seen in specific cases, but to get the complete generality, I need this. Okay, now look at, consider the same situation as before, but now assume that our set S here, which was previously depending on x1 up to xn and x, does also depend on the point configuration phi. So we can take into account more information, if you like, in the neighborhood. But we do this in a specific way, namely we assume that this S is, with these arguments fixed, is a stopping set. Otherwise, these assumptions are the same as before. I forgot one thing. It was too late to correct it. This Rm depends also on the Poisson process, but it's not. We have to assume that it is measurable with respect to the so-called stopping sigma field. I haven't introduced it. Stopping sigma field. So otherwise, it's just the same, and the result is the same. So as in this optional sampling theorem, or in this rather Nicodim derivative thing, the result remains just the same. It's just the same. It's the same parameters, and just the proof. It's a little bit more elaborate. At least I don't know how to do it without using this rather Nicodim change of arguments thing. I got 10 minutes. I would like to tell you a little bit about flats, Poisson processes of flats and associated tessellations. In stochastic geometry, there are two basic models for tessellations. Now we have a bigger zoo of tessellations, but still these two tessellations are very fundamental. The first is the Voronoi tessellation, and it's dual, by the way, the Delaunay tessellation. The second one are Poisson line tessellations. So what's the idea of Poisson line tessellations? You throw lines at random in the plane, okay, and they are forming a tessellation with very specific properties, by the way, geometric properties, because you are throwing lines in the plane like this, for instance. Okay. I will explain in a minute how this can be formalized. Many of you know, I'm sure. And you see, in contrast to the Voronoi tessellation, where each vertex has degree 3, or d+1 in arbitrary dimension. Here, each vertex has degree 4. So it's a geometrically very different picture. Anyway, it's a well-known model, and it has been used, for instance, by the colleagues in Ulm, also to model some streets or whatever. I would like to mention that everything what has been proved for Poisson Voronoi tessellations can be formulated and proved for Poisson line tessellations as well. Once you have the technology, you can do this. So what is a Poisson flat processes? I'm sorry for the jargon, but people in stochastic geometry are using this. They are calling a K-flat just it's an affine subspace of Rd. So it's a shift of a k-dimensional linear subspace, and it's called AD. This dimension K is dimension of the flats, and this is the Grassmannian. This is the subspace of all linear subspaces of Rd, subset. So these spaces are very nice. You can give them very nice topologies. They are beautiful spaces. And so because they are nice, you can just play the usual games. You can introduce Poisson processes, or more general point processes, on this space A. There's a notion of local finiteness here, but I skipped this. And a point process is called stationary if it has the same distribution, if the phi has the same distribution as the shifted phi, where the shift now is acting on the flats, of course. So any flat of the Poisson process is shifted by the same x. And the intensity of such a Poisson, or of a stationary processes of flats, is just given by this number here. You count the number of, let's say, hyperplanes. That's the case which is of importance in the last 5 minutes. You count the number of hyperplanes intersecting an isotropic set, a unit ball. This is a unit ball. Normalize. You count this, take the expectation, and normalize by the volume of the unit ball in Rd minus k. It's the appropriate normalization. That's intensity. You somehow form the mean number of hyperplanes intersecting an isotropic set, a ball. And here's a result which is characterizing all intensity measures of stationary point processes of flats. And I have to mention this because Poisson processes of flats are forming a much richer family of Poisson processes than just the stationary Poisson process on the line. Why is this so? This is so because you have a directional distribution. I mean, for instance, you could choose your lines just in 2 directions. With probability p, you choose a line in this direction, and with probability 1 minus p, you choose another direction. But you can think of any possible distribution of directions. So, and this is this Q here. It's called directional distribution of the stationary processes of flats. It's not too difficult, by the way, to recognize the intensity measure here. So there's a little bit of work here because the translation RD is not operating properly on the spaces of K flats. So the stabilizers are non-compact. That's the reason. So we have to work a little bit, but basically what this Q is the directional distribution. So it's a much richer class than just stationary Poisson processes of points. Okay, and a Poisson process is then actually stationary if and only if its intensity measure is a multiple of such a thing here. Okay. You can generalize the notion of a stopping set in this setting. I skipped this. And you can do the same thing. Instead of writing x1 up to xn, I'm writing now f1 up to fn for flat. And I'm choosing n flats. This is still the general case, so I'm choosing n flats. In the Poisson process, summing up over all f1 up to fn, and all the other things are just the same. The difference here is, of course, that instead of looking at the volume, I'm looking at the intensity measure of the set S. I have to do this, okay? And you see now you get even a force parameter. You have the m, you have the n, d minus j d. Everything is as before, but here you have the codimension of the flats, d minus k. So let's look briefly at the hyperplane case. So in this case, we have a stationary Poisson process of hyperplanes. These are affine subspaces of dimension d minus 1 with intensity measure a multiple of, maybe I should mention this first, sorry. There's some interesting integral geometric thing here going on. Namely, lambda q is a measure on this space here. If you are forming the measure of all flats intersecting a given closed set K, then you expect this thing to describe certain geometric properties of K, at least if K is convex, okay? And indeed, if Q is the uniform distribution, so if any direction has the same probability, then this guy here is proportional to the surface area in case k equal to 1. It's a very, very old fact. You can measure surface lengths in 2 dimensions as the invariant measure of all lines intersecting the set. It's a very nice fact, by the way. Or if you take hyperplanes, then what you get is the mean breadth of K. If Q is not the uniform distribution, then this is some sort of generalized integral geometric content. Okay. So, and because of this, we get the results here for the hyperplane things, because in this result here, okay, what we actually do is we look at set of flats intersecting a certain set. So this is giving us some integral geometric measure. So in the end, at the end of the day, we get, because of this here, we get the gamma distribution for, conditional gamma distribution, for the generalized integral geometric contents of some random set. So here are here's the case of the Poisson hyperplane, So we have hyperplanes in the space with directional distribution Q. And you see here we get a tessellation. That's just a definition in a general dimension. So the complement of all these hyperplanes is made up by polyhedral sets, and the closure of these cells are forming the well-known and very useful hyperplane tessellation, and we call it X. So 3 examples, and again miles must come first. So pick one of the cells at random. Okay? So here, pick one of these cells at random using Palm calculus to make it rigorous, and you are forming the in-ball of this cell. So this is, it's not unique, but the radius is unique. And the radius, this is not good. It's okay, it has an exponential distribution, but it's much more explicit because this is a ball. This generalized integral geometric content is just a diameter. I'm sorry. So the result is it's a misprint. It's correct, but it's not very helpful. The diameter or the radius of this in-ball of a randomly picked cell of the hyperplane tessellation has an exponential distribution. Has been proved by Miles, or at least he gave some hints how to prove it. Another example, pick an edge. No, I'm sorry, it's okay. I'm here. The radius is exponential distributed. It's okay. Everything is okay. Pick an edge of the hyperplane tessellation at random. Then this generalized integral geometric contents has an exponential distribution. It is the length in case we are in 2 dimensions, and Q is the isotropic distribution. Okay. Pick a point X on the edges at random, now with respect to one-dimensional Hausdorff measure. So we choose a point X according to length, the length measure here. Okay. Then we also have gamma distribution, as you might expect. We don't need to condition here, but this is again a spatial version of the waiting time paradox. So we have a gamma 2 distribution, while here we have a gamma 1 distribution. And there are many other examples. Just here recently, just now we are discussing other examples of stepping sets. I hope I could convey some picture of what's going on here, and that's basically all what I wanted to say, because I have mentioned the references already. Thank you.
I mean, part of the arguments, like the stopping set or the moment measures, would extend to Poisson point proceed with an arbitrary intensity measure. So, is there like a possible generalization of these gamma results for this class of processes?
I don't know, and I don't think so, because if you have if you are dealing with stopping sets and with just scaling properties, Sergei has shown to us how to do it. Okay. But if you would like to work with the geometric properties, really, as in the case of Poisson Voronoi tessellations or hyperplane, you need translation invariance to make the arguments working.
Well, I don't mean for gamma distribution themselves, but for some sort of class of functions which would be defined with respect to the intensity measure.
If you don't think of gamma distributions,
no.
of course, okay,
that was
then
of course not gamma.
Yes, then many things, many calculations just carry over this change of measure thing and Meckes-Liebniak and things like that. Yes. Actually, we are working in Karlsruhe on partially stationary tessellations. Tessellations on the torus, for instance, or tessellations even on RD, which are only partially stationary. And there is a way to define typical objects, a more smart way, and there are mean value formulas and things like that. So many things can be done. But for gamma distributions, it's very specific to Poisson processes and to this kind of invariance properties.
So in the cases where you get the gammas with integer parameters, is there any meaning to the underlying decomposition as sums of exponential?
That's a good question. I could forward this question to our friends again. I mean, in trivial cases where you have this growing ball, okay, so you get more and more volume, and the increments are then independent and exponentially. But in more fancy cases, as the ones also, the question is, it's a very, also somehow it's suggesting itself.
Yeah, for the vertex.
Is there a decomposition? And it's not easy to say.
No, it's not true to say.
It's not true.
Yeah. For instance, for the Voronoi flower, you expect that since it's gamma distributed with a number of particles that construct the Voronoi cell, right? And so, but the gamma distribution is the sum of n exponential distributions. So, can you decompose actually the Voronoi flower into n exponentially distributed domains? And it seems to be no.
I think for the vertex of the Voronoi tessellation, that looks particularly interesting question. That's where you get d+1, right?
Yes.
So is there some geometry there to that d+1?
I'm not aware of. Also the further that if you increase the m, then that's clear. But how to get the d+1 really as a sum, I don't know.
Okay.
Some related questions. Since Venkat mentioned that, I was thinking of growing the ball. You get independent increments,
Yes.
right? So you get the Levy process.
Once you have,
Uh,
let's say, the
Fixed.
time setting the first points, and then you continue growing, then you get
right.
just the,
So,
you just parameterize the Poisson process radially,
Right,
and
right.
then you have a Poisson processes of distances.
do you know any other examples where you can compute joint distributions by moving, let's say, the center of the ball or by? I said.
So Takis is asking for, what are you asking? You are asking for joint distributions. There's again a classical result, I don't know whether this will answer your question, but there is again a classical result by Roger Miles saying the following. Actually, these gamma distributions result, they are more general. You can come up with some distributional properties which are independent of the volume. But anyway, Roger has done the following thing. He picked the vertex at random, and then first what we have seen now in the talk is just that the volume of the ball containing, let's say in the plane, the three neighbors. Okay, but you can then ask, what is the distribution of these three directions? What is actually the joint distribution of these three directions and this radius? And there is an answer, a geometric answer. You have to form the area of these simplices, and this occurs as a weight, as a density with respect to the completely independent, to the distribution arising from choosing the directions independently. And once you have this ball, outside this ball, because of a stepping set property, everything is Poisson. No problem. So the pi probability, so to speak, is just changing this pattern locally. Outside this random set, everything remains Poisson.
Okay, maybe one more question. Okay.
One more question. So your function R is basically indicator function that the domain is M-filled in the terminology of Miles. But
Sometimes it's a little bit more, but yes.
yeah, so that's the question. So can it be something that is more? Can it be
Yes.
just a function rather than just indicator function? So could it be a weight function, for instance?
It's allowed. It's allowed.
Okay. Maybe we stop discussion at this moment and. Sorry. Thank you.